So what we're gonna do today is to talk about new thing. It's a version that I call it Leaky, expanded decomposition and hierarchy. Okay. So why we are talking about this? Well, so like last time we see we basically have seen how to do n square max flow, right? But in this algorithm, we actually assume two things. There's some assumption, and we want to remove that assumption today. Yeah. We will not completely remove it. We will actually reduce it to some flow subroutine, and then next class we will finally solve that flow subroutine when we are really done. Okay. So that's the goal for today. And so how? Well, I will introduce you to like a new structure, which I call Leaky, expanded decomposition and hierarchies, and then how to construct them. And then you see that like a lot of complication that we want to do, is simplified with this thing. Okay. Like first of all, I just need to tell you what is this thing. What is Leaky expanded decomposition? So, okay. The first concept is component constraint expansion. Okay. So what is this? Let me tell you first about component constraint demand. Okay. This is simple. So basically, I said that suppose that I have a graph H. Suppose that I have a graph H with, okay, right. H can look like, let's say even in unrelated graph, yeah. Let's say H looks like this. Then demand is just like a demand to send flow between pairs, right? And this demand D, like is H constrained, like is constrained by component of H. If I can only try to send flow between connected component, between nodes in the same connected component of H. So basically, I forbid it from trying to send between this thing.
H is like a.
H is like a subgraph. H is like a graph. Think of Later we will think of H as a subgraph, but H is just a graph. Yeah, it's just a graph. Let's say I call it G. That can be right as G too. Yeah. H is a graph, and demand is H constraint if we only try to send positive demand between UV only when U and V are in the same strongly connected component of H. For example, if you have this, if H look like this, if this is the graph H, then there are two strong components. Then the demand that is constrained by H is just only between nodes here or node here. You cannot send between this guy, because these two groups are not strongly connected. Okay. Okay. So this is I'm just defining what it means for demand to be component constrained by some graph. Just mean I have demand only between pairs that are in the strong connected component. Now we can just talk about component constraint expansion. So when we have a node weighting A, so note that A is phi expanding in hash. It's just the same thing as saying that every A respecting hash constraint demand is routable in hash with congestion 1/phi. We have always been like kind of talking of like kind of implicitly like assume this, because recall our convention. Recall this convention. When we said that A is expanding in some graph hash, we basically said that for every connected component U in hash, A in U is expanding in the component U. Okay. Yeah.
Does this create any requirements for like the structure of H? Like, does H need to be an expander for? Like,
no, right? This is really this. There's no nothing. There's no requirement about hash at all right now. Okay. It's just like I kind of try to introduce one new word. That's it. Yeah. Okay. 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 So you see that like when we say that A is expanding in hash, it just means our convention is just to say that for each component of hash, A is expanding inside that. Now like we can kind of formalize it with this word. Just to say that for every A respecting demand, that is also hash constraint. So we only try to send flow between same components of hash. This demand is routable with low congestion. Okay. So this is just to kind of put this word into the context of previous notation, previous terminology. Okay. Okay, now here's a new notion. Suppose that I have think of hash as a subgraph of G of some other graph. Then I can actually now talk about I can say that A is hash constraint phi expanding in G. This thing just means that every A respecting demand that is also hash constraint is routable in G with low congestion. Okay. For example, suppose that the component of hash look like this, but maybe these are component of hash, right? But maybe the graph G has more edge here. Let's say the graph G has more edge, one more edge. Okay. So if G would have one more edge, so okay, if it's like this, then if I said A is hash constraint phi expanding in G, it means that for any demand between the same component of hash, I can route, and I can route using edges in G as well with low congestion. But I only try to route demand between same component of hash. I never try to route between different a pairs between nodes, a pairs of nodes on the different component of hash. Okay. So do you see that if I say that A is expanding in hash and hash is subgraph of G, it just implies this. So because this just means that I can route things in the subgraph. This just like here I just allow more connection. Yeah. Yeah.
So this kind of looks like the picture pre-expander trimming as well.
Exactly. Yeah. Exactly. Very good. Yeah. It's just like something is kind of before we do expanded trimming, like A is kind of expanding in that large giant component, but it's expanding in G. Yeah. Very good. Yeah. Okay, so let me compare it more explicitly again. If H is a subgraph of G, if A is expanding in H, then A is H constrained phi expanding in G. So that's just from definition. And just to be clear, the other direction doesn't hold. Okay. And for example, let's say that H, like I even write it in undirected graph, but like this doesn't hold in undirected graph too. But the example is undirected. Okay. You can think of this example to be directed just by adding like bidirectional edges. Yeah.
Sorry, why does the left-hand side imply that A is H constrained?
Oh, because when we say that, like, when A is phi expanding in H, here, right? It means that any H constraint demand is routable in H.
Oh, okay, gotcha. I see. Okay, great. So this is just your, like, okay, yes, good.
Okay. Like, when A is expanding in H, we just try to route demand that is H constraint, and this is just routable in H. And here, when A is H constraint phi expanding in G, we try to route demand that is H constraint too, but we now can route in G.
Okay, so this is like a slightly different definition of like phi expansion that like is used for directed graphs, I guess. Is that is like that the way that it's different from what we were talking about earlier in the course?
It's quite the same. So I'm not sure what you mean.
Okay.
Like, it's just to kind of say that this expansion, like, when we say that this expansion is constrained by H, okay. It just kind of say that this expansion is weaker according to H.
Yes. Yes. Okay.
Yeah.
Good.
Like this thing is not adjective of A, but is adjective adverb of this thing.
Okay.
Yeah.
Gotcha.
Yeah. Okay. So let's see why like another direction doesn't hold, right? So here, well, like A is not expanding in H because H here is just a path. And clearly there is like a sparse cut on at the half of H. But A actually is H constrained phi expanding in G. Because whatever demand like on A that is H constrained, so like any demand here, really, you can just route through the clique. So like because you can route on G. Okay. Any demand, if suppose that I want to send plus and minus here, you can just route like this. Yeah. Just because it's routable in G, but not in H. Okay. Is this clear?
So this is an undirected graph then?
This is undirected graph. You can make it directed. Just for example, just make every edge bidirectional.
Okay, good.
Okay. So one simple observation again is like if A is H constraint phi expanding in G, then if you look at any subgraph H prime of H and any supergraph G prime of G, A would be H prime constraint phi expanding in G prime. Okay, so let's see why. So first, H prime is more constrained. H prime is subgraph. There are like the SCC, the strong component of H prime, is even more fine-grained. It breaks component. So there are even less demands to consider that you need to route with low congestion. So whenever this is a subgraph, it's just easier to be expanding. So if H prime is empty graph, then basically you don't need to route anything. Like A is empty graph constraint phi expanding in any G, for example. Constraint. If H is empty, then there is nothing to route. Okay. So also next, G prime has more connection. So if it can route in G, then it can route in G prime too. Okay. So I hope that you get familiar with this concept. It's like a component constraint expansion. Okay, now I can define this new concept, which is Leaky, expanded decomposition, and hierarchy. Okay. So let's recall what's the notion of expanded decomposition. Okay. Is that like a phi expanded decomposition of A in G with slack kappa is just a H set C such that, well, after removing C, then A is phi expanding. And the size of C is at most phi times A with slack kappa. Okay. So we've seen that there exists, for example, expanded decomposition with slack log n. There exists this thing. We have faster algorithm where slack is worse than log n, like log cube or something like that. Okay. Okay, this is just an old notion, nothing new. But one thing I want to kind of observe is that suppose that I have, if we look at any component U in G minus C, right? Then, and then like, let's say that, oh, sorry. I mean, A intersect U, yeah. And let du be A intersect U respective demand. So let's say like, look at this component and look at the demand in between A here. Yeah. And then like, you might have like a U1, U2, yeah. And there are like demand between A here, demand between A here. So, like, we know that du can, like, given du for like demand on every component U, given du for all components, all of this du are routable simultaneously in G with low congestion. So nothing happened here, like, because just A is routable, A is expanding, so demand on A is routable. And the demand here would be like kind of routable inside the component, right? Here it's like, it might route like this, but it's just inside the component. Okay. So given demand on every component, you can route inside the component. That's expanded decomposition, the old thing. Now here's a new thing. Leaky expanded decomposition. Okay. So leaky phi expanded decomposition of A in G with slash kappa is almost the same. Like you have the size of the cut is phi kappa A, the size like before, but the expansion now is different. The expansion is that A is G minus C constraint, phi expanding in G. It's G minus C constraint expanding in G. Okay. So let's try. Let me like this observation would like let me observe one thing again. Okay. So if you look at any component U again, and you look at the demand, on the component U, demand that respect A in the component U. Okay. So now let me ask you this. If I given all the demand for all components, like before you have demand between A here and A here. Okay. Is it true that all the U can be routable simultaneously in G with low congestion? Is this true?
Not necessarily, because we're allowing routing outside of the component, so there could be along like some like sparse cut in G or something.
Okay, so you said that right now you have this demand, and now like you kind of might route outside the component. This thing might also kind of route outside the components. So the congestion caused from here and the congestion caused from demand here might interfere with each other, and the worry is that they might have large congestion. But actually, it will have low congestion. Yeah.
Because like you can sort of say in the same connected component in G or in C, sorry, when you're like have like this sort of demand that like you need to sort of route to other expanders in the expanded decomposition.
So yeah, I mean, I want to say that my point is, it's indeed true that here, if we guarantee this thing, when you try to route demand, you can route outside your component. But just from the definition of this guy, it really just says that given demand on every component, or at the same time, you can route all of this guy with low congestion. That's the definition of this guy. Right? This is really kind of definition of this. Here, like it says that given demand that respect the component here, meaning that given demand that only demand between the same components, you can route this demand in the whole graph. You route this demand in the whole graph with low congestion. Okay. So yes, it's still true. This is still true. But the point is that the flow here can leak outside the component. But no, although they leak, we just guarantee from the definition that they altogether they have low congestion. Okay, so this is a concept like This is kind of the explanation why I use the word leaky. Okay. Previously, given demand on every component together, you can route them separately. Here you can route them too. They might interfere, but still with low congestion. Okay.
So in some sense, we're not leaking like too much flow.
Yeah. The flow might leak, but not too much to cause too much congestion. It might leak really a lot. So actually, it might leak a lot, but it leaks in a way that they don't overlap, like to cause congestion anywhere. Yeah. Okay. So we can talk about leaky. We can try to define leaky expanded hierarchy as well. If I have an expanded hierarchy, okay, just to recall the old concept that the expanded hierarchy is just a partition of H set, right? Such that EI is expanding in G minus all the edges from level above. For example, EL minus 1 would be expanding in G after minus edges from level above EL. So from when you subtract EL. So this demand between this guy is routable here. Demand here is routable inside the component. Okay. Now leaky SE hierarchy is just almost the same. Just the same partition, but now EI is G minus E more than I constraint expanding in G. Meaning that given any demand between the same components, given any demand between like EI in the same component, you can route. You might route outside the component, but it has low congestion. Okay. So demand between the separator here, you can route it simultaneously for every component, but with low congestion. Like here, you might, for example, route. If you want to route from maybe A to B, you might somehow route it like this for some reason. Yeah. With low congestion. Okay. So I hope this is clear. Okay. We can talk about expanded hierarchy of a subgraph too. Like I said that this is expanded SE hierarchy of subgraph in G, subgraph G prime in G. If now it's just a partition of edges in G prime, and E prime is just G prime minus E more than I constraint expanding in G. Okay. So the point is like, it's just like before, but like now I allowed, it's just like the constraint is for G prime like before, for the original graph like before, but I can route in the supergraph, for example. Okay. Just so even more relaxation. Okay. Anyway, this is just terminology. We will look at it soon. Just one note is that in case you want to look up literature, people use the term weak instead of leaky, but the term weak sometimes refer to many different things in the literature, and it can be confusing. So I just use the word leaky here just to be really descriptive and specific to this notion. Okay, now the point again is that this leaky thing is just much easier to construct, and it will be good enough for our Mac flow in n squared time. So let's try to construct it. So let me tell you how to construct leaky SE hierarchy. So before we have seen how to a top-down algorithm for constructing SE hierarchies using expanding balance separator, find the balance separator, recurse. Right? That's just work. Today we see different one. It's bottom up, but kind of work only for leaky version, but it's simpler. And you'll see, we'll discuss in details what's like really important advantage of this approach. Okay, so this is the thing that we want to construct, a leaky SE hierarchy. And here's the algorithm, a really, really simple one. Okay. First, I just initialize something simple. I let C0 be all the H set. And then I start with I equals 0 and let phi be something like 1/4 kappa, where kappa is like a slack of ED, a slack of expanded decomposition. So think of kappa as like log n, for example. This is like existential version would be log n. If it's like fast algorithm using cut matching game, kappa would be log cube. Okay. Okay, so the algorithm is here. Start with C0 to be all the H set. Then we just compute phi expanded decomposition of Ci. Let this be Ci plus 1. Then increase I. So Ci plus 1 have size something like, by definition, something like phi kappa times degree of Ci. But kappa, like phi is chosen so that like this is less than Ci over 2. Okay. We just choose kappa to be like kind of cancel, like we just choose phi to cancel with kappa and add like a factor to like get a half here, get half factor here. So the size of Ci plus 1 is kind of half just by a choice of phi. So Ci plus 1 shrink, can shrink at most log n times. And at some point it's going to be empty. That's it. That's next. We just return EI. Okay. What's EI? EI is just all the edges in Ci. That like think like this. EI is all edges in Ci that is not promoted to the next level. Like think like you start with edges at all of them at level 0. Some of them will be like everything at level 0. Some of them will be promoted to the next level. This is like a C1. Then if C1 is expanding already, then C2 would be empty, right? Because you compute expanded decomposition of C1. If C1 is expanding, C2 will be empty and you're done. If C1 is not empty, it's not expanding yet, then there might be like some cut C2 that you cut so that C1 on this component and C1 on this component is expanding after cutting C2. And all the edges here is basically you think like it's promoted to level 2. And then you have C2. You ask if C2 expanding yet. If not, do expanded decomposition, cut something, promote to level 3. Okay. At some point, you will stop. And the edge, EI, is just edges that is promoted to level I, but not further. Is it clear? Is the algorithm description clear? Good. Okay. So it's just clear from how we define that there will be log n levels. Just how we choose phi. All I need to tell you is just why this is expanded hierarchy. Yeah. Okay. Why is it the case that EI is phi expanding in G minus E more than I, but not quite this. This would be SA hierarchy, not leaky version. We want to just say that this is like when you just constrained by the component of this guy, EI is expanding in G. That's what we want to prove. So we want to prove this. EI is expanding when you constrain by the component of G minus EI plus E more than I. It's expanding in G when you constrain by this component. Okay. Let's see the proof. The proof is simple. First, just from the guarantee of expanded hierarchy when you compute this step, right? Ci is just expanding in G minus Ci plus 1. That's just the guarantee of expanded decomposition. Okay. So, but then just from definition, this is like 2x to be expanding. And then I can just write that this is the equivalent to Ci is G minus Ci plus 1 constraint expanding in G minus Ci plus 1. So, but it means that this is just expanding constraint in G. Sorry, it's constraint expanding in G. Okay. Okay. But now you know that EI is a subset of CI. Okay. So because EI is defined to be CI minus CI more than 1. So it means that you can actually write this, replace this by EI. This is just all H at level, like that it has been promoted to level I, but maybe more. But this is all edges that kind of promoted to level I and not further. Okay. Okay. So EI is expanding in G minus C, like is expanding in this with this constraint too. Okay. But then but G minus C is subset of G minus E more than I. Okay. Why? Well, like E more than I is just the same as C more than I, right? Like these are just all edges that are promoted to level more than I. The same thing here. Okay. So yeah, so this is clearly kind of less than this, like it's a subgraph of this thing, which is the same as E more than I. Okay? So it means that EI would be constrained expanding in G. Because this is a subgraph of this guy. So you have more constraint. Okay. Okay, so you get this thing. So let's see this in, this is a bit symbolic. So let me drop some picture. Okay. So you have a graph G, and let's say that like this is your CI. Yeah. And what we have is like, okay, we do expanded decomposition with respect to CI, and then you get maybe like you get CI plus 1. Okay. Thing like CI plus 1 is like a smaller, doesn't really matter. But what is CI plus 1 say? It's just to say that, okay, this thing is expanding in this part. This thing, like CI in this component is expanding in this part. And the same is true here. Okay? But then you might have like a CI plus 2, CI plus 3, and so on. Like you might have like more edges, like a cut that go to further level. Maybe like whatever, like this and this. Let's say this is like a CI plus 2, just more any C that more than CI plus 1. Okay. So what do we have? What do we need to say here? We just need to say that, like, now what's the component? What's the component in EI, which is G minus C I plus 1 minus C more than. Yeah. We just need to look at this component. Like you have this component, you have this component, you have this component, like just all the components that are created by blue and red. Okay. We need to say that the green thing inside each component, like each black component here, is expanding is expanding. But it might not be expanding in this component. It might go out. But for example, like you know that, like maybe call this thing, this part, like A and B. Yeah, A and B is expanding in the red component. A and B would be simultaneously expanding, but not in the black component. But it's actually expanding, like it's expanding simultaneously. Okay. So the flow between A and the flow between B can be routed simultaneously with low congestion. Okay. But it might go out of black component, but it still respect the red component. Okay. So you see, like E, when you only try to route between the components of this guy, you can route it in the whole graph G with low congestion. Hope that makes sense. Questions about this?
Just over in the picture, so you have demand between vertices in A,
Yeah.
vertices in B, but not between A and B. When you like.
Yeah, at least like from what we want to prove here, I don't want to route between A and B. But even if I want to route, I can. But like, so I try to prove something weaker than what I can do.
But you cannot go through the red component.
It will not go through the red component. Like if I want to route between guys between like on the different red components, maybe A and C here. Now, I will not guarantee.
Okay.
But all we need to say is like even like we want to route, we kind of get guarantee that demand between red components can be routed with low congestion inside red components. And now we just need to route demand between guys that are kind of more fine-grained than red components. So that's even easier. Okay. Good. But once we have this, we are done. This is just the definition of leaky SE hierarchy. Right? So we get it. That's it. It's super easy. Okay. So further, I want to kind of look even further. If you look at the proof, we don't quite need this step. Or like I need this step to conclude the proof. I just need that Ci is G minus Ci plus 1 constraint expanding in G. Can you tell me how can I relax the algorithm if I only need this?
Instead of a phi expander decomposition, you can have like a phi like E greater than I constrained, or G minus E greater than I constrained expander decomposition.
Yeah. Like basically, we can just use a leaky version of expanded decomposition. Because this is all we want. Leaky expanded decomposition guaranteed this exactly. Okay. So we only need this, so just use leaky expanded decomposition instead. Okay. So leaky SE hierarchy only require leaky expanded decomposition. Okay. So to conclude, if we set phi to be like this, okay, something like 1 over log, you can build leaky phi SE hierarchy just by calling leaky phi expanded decomposition log n times. Okay. Okay, so now let me discuss a bit about the advantage. So this looks simple. So that's one thing, but what really is the advantage? The crucial advantage of bottom-up approach is this. Let's look at the time before I actually try to compute expanded decomposition of Ci. Before I kind of compute Ci plus 1 here. Look at that time before I finish the algorithm. And let Gi prime to be the graph when I remove Ci. Now, when you look at the graph after removing Ci, so the edge that has been promoted to level I, they are basically left with edges with level that has been promoted to level less than I. Okay. So let's say that E prime j is just all edges at level I that has been promoted to level IN but not above at that time. See, I plus 1, I plus 2 was not computed yet. I just look at this edge at level j but not above. Not above to be Ej prime. Here's a key observation. These edges from level 0 up to I-1 at that time, it actually just already form an SE hierarchy of this graph. Okay. Why is this? Well, like obviously this thing form partition of edges of this graph because this graph have like all edges except the guys that has been promoted to level I, and we have this is just all edges at each level. Okay. So that's the partition, but the expansion guarantee is there too. Like just from the same proof, really the same proof, we know that Cj is G minus Cj plus 1 constraint expanding in G. And then from the same proof, really, like you get that E prime J is Gi prime minus E prime monoid J constraint by expanding in G. Okay, I will not go over this, it's kind of the same proof. What's important is like you just need to observe that the edges from level below I so far, just from an SE hierarchy, when you try to compute expanded decomposition at level I. Okay. What's good about this? So before computing expanded decomposition at level I, you have SE hierarchy of edges of level less than I. Okay. So it's like we basically can try to use and exploit this hierarchy to speed up the expanded decomposition computation. Like we have seen once, for example, like in MaxFlow algorithm, that if you are given SE hierarchy, you saw how to speed up MaxFlow, how to make MaxFlow fast like an n square instead of mn. So this is here is true here too. Like you want to compute some expanded decomposition, you basically have the hierarchy structure given to you because we have been building it bottom up. And you can try to use this hierarchy to do expanded decomposition to build the next level of hierarchy. So this is a kind of bootstrapping idea, okay? Just in other words, let me say it again. We basically can use the SE hierarchy up to level I-1 to help us build the next level of the hierarchy. Okay. Like we get this SE hierarchy up to level I-1 because, yeah, this thing is, yeah, this is what I mean here. And we build it, we need to compute this, the expanded decomposition at level I, just to build it to the next level. So that to get the hierarchy up to level I. Okay. This is basically the key advantage of bottom-up construction. That is quite different from top-down. From top-down, when you try to compute, imagine that algorithm, you try to compute balance separator, you kind of have nothing with you. You just try to do it from scratch. Okay. Here, like, when I try to do it like at the bottommost level, okay, I have nothing, but it's just about doing expanded decomposition with respect to degree. And that we can, that I should have said that, like, when you try to do expanded decomposition with respect to the whole graph, that's kind of easy. That is something that push level can do for you. You see, like, push level you can use to find sparse cut with respect to degree. Okay? So that's in the top, the bottommost level, you can easily use push level. Now, like to do next level, it's not the node weighting is not degree node weighting anymore, but you can basically have SE hierarchy from below. That's useful for you. Okay, so just to conclude, what we can say is that we just, in each step, you just need to look to compute leaky, expanded decomposition, but you also promise that you get expanded hierarchy of edges except of the graph that is not in CI already for you. Okay. So that's kind of what we have for leaky SE hierarchy. Okay. Just some discussion for top-down algorithm. You saw it before, how to build SE hierarchy top-down in underrated graph using expanding balance separator, and it just used polylog MaxFlow. This should generalize to the rated graph too, and somehow like right now the state of the art is that no one did this yet, and I think you can do it for sure. Yeah, using content from this graph, content from this course. Yeah. So if you want to have some other project somehow, yeah, you can. Yeah. After this course, even. Yeah. Okay. So that's how you can compute leaky SE hierarchy. You see that it's simpler than just SE hierarchy. Let's look at leaky expanded decomposition. It's going to be simpler as well. So you see this algorithm for leaky ED, which is simpler and faster. Okay. So let's recall. This is what we want. This is what we want to do. Given directed graph, A and phi, I'm gonna compute the cut C, such that, well, like the size of the cut is like phi log n times A, and A is G minus C constraint phi over log cube expanding in G. And the algorithm will take like the time for this balance cut or giant expanding set subroutine times log m times log n. Okay, so basically it gives leaky phi ed with slack something like log to the fourth, right? Because there's one lock here and lock cube here. You can scale things so that this looks like 5 and this looks like log to the 4th. Okay, let's see this algorithm. So before doing that, let me recall quickly algorithm for expanded decomposition, which is we use 2 subroutines, right? One is just this balanced sparse cut or giant expanding set, which is like it finds some sparse cut that is either balanced or it's not balanced, but the complement is expanding. We have seen this. Another one is expanded trimming. Okay. I will not go over this. But the algorithm is just first call this thing like balance or giant expanding set. If it's balanced, then recurse on both sides. Return a cut here and recurse on both sides. If you get a giant expanding set, first you trim and then recurse on only small side. That's algorithm. Okay. Now let's see how Leaky expanded decomposition algorithm is simpler. By the way, like the balance here, I need to set it to be something like 1/8 log cube, like log square here. This log square here is needed so that when you trim, you don't trim too much. So the balance is not quite balanced. It's just something like 1/log square. Here, the Leaky version, I'm just going to do the same, but the balance parameter is 1/8. It's better. And if I get a balance cut, just recurse on both sides like before. If I get a giant expanding set, then I don't trim, don't need to, and just recurse on the smaller side. Just keep expanded trimming. And that makes total sense, right? Because we kind of want to be expanding in the graph. We don't need to be expanding in the component. You just keep trimming. The fact that we keep trimming, we can set the balance to be better. Okay. So analysis is just going to be the same like before, like expanded decomposition, just only simpler. Everything is simpler. Each component, when we recurse, has size at most 1 minus beta. Here is just kind of 7/8 fraction. And this is kind of trivial because in the balance case, both sides is like small. Both sides is not too big. In the expanding case, we only recurse on smaller side. So that's kind of trivial. But now the recursion depth, which is used to be something like 1/beta times log n. Previously, like it used to be this thing. But now the balance is better. So because now balance is constant, so you get log n. The recursion depth is better. The total time, you literally just call this thing once per level. There are log n levels, so the running time is this. The cut size, we know that our cut here is just a union of edge crossing sparse cut. Like previously, we need to say that we need to prove something, but now this is trivial. And so if C is a union of edge crossing 5 sparse cut, like, okay, this is trivial because like C is just a cut crossing our balance, like our balance or expand subroutine, right? So once we have this, you just get this bound from the old charging argument. that each smaller side is charged log n times, something like that. Expansion, when I say that here is a less trivial one. When I say that A is G minus C constraint, phi expanding, phi over log cube expanding in G. Okay, so let's see the proof. If I look at each component U, okay. When you return U as a component, that's basically U must be giant expanding set in some calls of your subroutine. Right? If you get a balance cut, you would recurse. You wouldn't return it as a component yet. Only when you fire a small cut and you just say that this is your component U. The U is going to be giant expanding set of some call of this subroutine. So it means that A intersect U is phi over log square expanding in G, not in G of U. Okay. So can I just say this? That A is G minus C constraint expanding with this factor. Why can I just say this?
Because like our guarantee across like all of the components only applies when we've had like one call to the sparse, and we have like up to log n, so we don't necessarily know that it routes nicely.
Exactly. Like this guy is just kind of expanding in G and can go in this way. But now like the guarantee of bar cut or expand is just kind of guarantee for one component here, not for every component simultaneously. And like what we do is just to recurse on the smaller side. So like the flow the flow that you route from U can interfere with the smaller side, but there are like just log n recursion depth. So the interference is just like log n factor. So the congestion can grow by log n factor. So actually like because of recursion depth is log n, you pay another log n factor in the expansion. So you pay log cube here. Make sense? Okay. Right. So that's how you get this. You get leaky ED fast just by calling this thing. Okay. So what did we do so far? We basically see that leaky ED can bypass expanded trimming. It speed up and it simplify things. You can use this to speed up the algorithm that we learned in undirected graph too. If you just want undirected leaky expanded decomposition, you cannot do expanded trimming. And you can see that like, for example, because balance parameter is better, everything is going to be a bit faster. You're going to get like a speed up of at least log square running time. And some application indeed don't only need leaky expanded decomposition like what we just seen today. The leaky SE hierarchy only need this. Some other application only need leaky ED as well. I just want to mention the most recent application. We saw approximate max flow in undirected graph. Okay. The running time that we saw is something like this thing over epsilon square. The most recent paper shows how to do this. So like it kind of bring the log factor here kind of to be reasonable, to become more reasonable now. Okay. It's just log to the 9. Hopefully it can be better. Epsilon is just one epsilon here, not epsilon square. Yeah, I expect that maybe like in 3 or something years, maybe you can hope for like log to the 4th or something. But likely you need to improve cut machine game itself too. But anyway, so bypassing expanded trimming is good. It simplifies things. But it's even more crucial for when we work with directed graph. Why? Because expanded trimming in directed graph is not really quite well understood. We don't have a good algorithm yet, actually. So for general node weighting A, I don't know how to do it, actually. Although like in undirected graph, you see the algorithm that just make one MaxFlow calls. Just do it from the boundary and then you're done. How to do it in directed graph, I didn't think hard about this, but I think like it's cool. It's a cool question actually. How to do this? Okay. Even existentially, I think it's interesting. But when A is the degree node weighting, then like there are techniques to do this. Actually, you can have a look at this paper. They use the technique of dynamic push and pull relabel, not just push relabel. Okay. There is another paper here. Actually, it's first, but it's less clear, like harder to understand. And in undirected graph, we see how to solve this one using dynamic push relabel. When it's directed graph, there is this one, dynamic push and pull relabel. So the idea is like it's kind of push the relabel, but actually some node can reduce the level instead of nodes can only increase the level. Okay, so quite cool algorithm. Okay, you can have a look if you're interested. Yeah.
If you can do this for general A, what would that be useful for?
Good. So it would have. So right now, there is no almost linear time expander decomposition algorithm in the directed graph for any node weighting A yet. No, sorry. There is one, but like the guarantee is like you kind of need to pay the slack. The slack is not polylog. The slack is interlittle one. So if you can do this thing, for example, using some MaxFlow calls, you would be able to get slack to be polylog, for example. But yeah, I imagine that there should be like more application. Yeah. Okay. So why are we talking about this? As I said in the very beginning, the point is like we in like previous 2 lectures we saw n-square MaxFlow algorithm, but we assumed 2 things in that lecture. If you remember, like we assumed that we can build SC hierarchy fast. We didn't know how to do that at that day. And we assume that we can project flow fast. That is, given some flow from some shortcut graph that we define on that day, you can kind of project it down to a flow in original graph, kind of removing the star, if you remember, removing the stars from the flow, and make it run, get the flow in original graph without much more congestion. Now, these 2 assumptions can be reduced to the problem in the next slide using what we learned today. Okay. So these 2 assumptions that we assume from that day using today's lecture, you can simplify the assumption much further. Okay, so what's the problem that we're gonna reduce these two things to? Is this problem? Okay, let me tell you. It's basically like balance cut or giant expanding set. Maybe I should write giant expanding set. This is like a thing that we have seen before. We use it many times for expanded decomposition, but here I just need like a certified version. And I also have like some promise. Okay. Let me informally tell you what this subroutine is. Basically, it's given G and some H set F. What is this H set F? Think like here, like think of it as like a cut edge CI, where like when you want to compute expanded decomposition of CI, we want to compute expanded decomposition with respect to some edge set, right? When we build this hierarchy, okay? So F here is like the think of it as like a edge set CI. Okay, and the promise is like we are given SE hierarchy of a graph when you remove CI. That's a promise. And it's the same promise that like you saw when we try to build SE hierarchy bottom up, right? When you try to compute expanded decomposition of CI, you actually have SE hierarchy of everything below. This is the same promise. Okay. And what you need to do is just either like find sparse cut, is to find sparse cut with respect to F. And this is either balance or you get giant expanding set. But you get also a certificate for this thing. What do I mean by certificate? I mean we just embed an expander on top of this set. Okay. Just like in cut matching game, when you certify that some set is expanding, you actually not just report that it's expanding. You actually embed some expander from the cut matching game to the graph. That's a certificate. Okay. So I wanted a certified version of this. Okay. So okay. The more formal one is just this. Like I have a graph, some balance, parameter, F and phi. Then we get a promise that you get a expanded hierarchy of graph minus F. And let's say A is the degree node weighting of F. Then you get a sparse cut with respect to F. And this cut is either balanced or it's not balanced. But if it's not balanced, you also compute an expander X such that X kind of contain this set, contain the set that you want to say that is expanding, and X is routable in G. Okay? So you kind of embed expander that certify expansion of A minus S, A on the side of V minus S. Okay. Okay, so the way you think about this is just this kind of balanced sparse cut or giant expanding set, but you have a certificate of expansion, but I have this promise. Okay. That's what this is about. Okay. Now I claim that if I have this subroutine, which we will prove next class, then you're done. You can build the SC hierarchy fast. Why is that? Because you kind of just saw that from today, right? If you want to build leaky SE hierarchy, it's enough to just call leaky ED several times, just bottom up. And if you want to compute leaky ED, just need to compute balance cut or expanding set. That's just the only subroutine that you need. And balance cut or certified expanding is even stronger. So this suffices. Now the important, so given this subroutine, you basically get leaky SE hierarchy. But okay, the most important point that I didn't add is if you have leaky SE hierarchy, it's just actually enough for the max flow algorithm, like the n square max flow algorithm that we have seen. So this is the exercise actually good. To get n square max flow, just enough to use leaky SE hierarchy. Not just non-leaky one. Leaky version just works. Okay. So this is maybe something to look back into that lecture. So I hope that you see that if you have this, then you can build a hierarchy fast. Now, is this clear to you? If you have this subroutine, you can build a hierarchy fast. Yeah.
What do you need at runtime?
Whatever this runtime is, you're gonna get the same running time here, because this thing just call this thing like a kind of log n levels, right? And this thing just call this thing for log n times. So you kind of pay log square overhead to the running time. Yeah.
So if we did get m polylog n time max flow, would there be an advantage to using leaky ED here, or I don't know,
If there is a max flow that is fast already, what's other application of leaky ED?
Yeah.
Right now, there's gonna be other application like shortcut, but I didn't teach it. Yeah.
Okay.
Yeah. Yeah. So far, leaky version is useful for flow algorithm and shortcut, for building shortcut like offset, those kind of thing. Diameter reducing shortcut, you can have a look. Yeah. Okay. But okay, I said that I need this, this one need this promise. How can I guarantee this promise? It's the output is certainly strong enough, but I want to guarantee this promise that I have a hierarchy of G minus F. Okay. I might just explain this next time. Yeah. Okay. So the plan of the rest of the class is I will try to prove this thing. And then on Thursday, I will just kind of tell you what's beyond this course. Okay? What's interesting beyond this course. And then on Friday, I let you just ask anything about the area